Well, thanks for inviting me. And as was said, I'm gonna teach a mini course on integrable PDEs in the context of infinite dimensional geometry. It's called integrable PDEs, but actually it will mainly be only one integrable PDE, just because 3 hours is not much. However, the ideas and the methods that will be introduced, they can be used to study many other such PDEs. So the one we'll be mainly talking about is the most famous integrable PDE that's known as the KdV equation. So KdV stands for Korteweg-de Vries. So this equation, it describes waves in shallow water. So we have a wave. This wave is described by a function of one variable x. And it also depends on the time variable because the wave is evolving. And then the KdV equation is a PDE on this function, which we'll write in the following form. So we'll use subindices for derivatives. So u subindex t, that's the time derivative. So ut plus 6 ux plus u triple x is equal to 0. U triple x is the third derivative with respect to x. The coefficient 6 here is purely conventional. It can be made into anything you like, but we have to choose something, so I choose 6. So that's the main. Oh, okay. Yeah, I thought I was uncomfortable, but yeah, now I see how it's. Okay, so this equation we'll talk about for this 3 lectures, and we'll introduce different ideas related to this. And well, kind of the main point is that this equation can be considered as an integrable equation. We'll see what that means. And we'll consider different points of view on this. And as I said, well, these things that we'll discuss apply to many other equations, and you'll see how to construct such equations, but we'll mainly only talk about this. I really don't know what the background of people is, so I'll have to start with some pretty basic things. So if I'm too slow and annoying after this lecture, just tell me, and then next time I can go faster, maybe I could try. So today, well, we are supposed to understand this from the perspective of infinite dimensional geometry. But to do infinite dimensional geometry, one first needs to do finite dimensional geometry and understand that. And then these finite dimensional ideas, apply them in the infinite dimensional setting. So this is what we'll start with. So we want to discuss finite dimensional integrable systems, and that we'll do today. And the next 2 lectures will be on the infinite dimensional case, in particular this KdV equation. Today's topic is finite dimensional integrable systems, and this whole discussion will be in the context of what's known as Hamiltonian systems. So let me call this finite dimensional integrable Hamiltonian systems. So what we'll discuss what these words mean, what Hamiltonian means, what integrable means, possibly look at some examples and constructions of such systems. That's the plan for today. So First, let me just formally define what a Hamiltonian system is, then I'll explain where this comes from, why this is important. So the context for the notion of a Hamiltonian system is a symplectic manifold. So this will be a symplectic manifold. So symplectic manifold is the following thing. M here is just a finite dimensional manifold. Finite dimensional for today. In the next two lectures, it's going to be infinite dimensional. And omega here is a differential two form, and it's supposed to be closed. So the differential of that is equal to 0, and it's non-degenerate. And, well, I said it's a two form, which also means that it's a skew-symmetric form. Skew-symmetric. Non-degenerate means that, well, you can represent this two form with a matrix. The determinant of the matrix is non-zero. The kernel is trivial, all these things. And because, of course, because it's a non-degenerate skew-symmetric form, this manifold automatically has to be even dimensional, otherwise it's not going to work. Such forms will not exist. So, as I said, examples will follow a little later. To actually motivate this, we first will define the notion of a Hamiltonian system or a Hamiltonian vector field. So this is defined as follows. We take a function on our manifold, let's call that capital H. That's going to be our Hamiltonian function. So here we immediately start thinking about physics. In physics, this function plays the role of energy of the system. So then what we do with the function, we take the differential of that function, that's a one form. And then we have this omega. So omega is a two form. Because it's a two form, well, you can plug in two vectors into there, get a number. Another way you can think about omega is it's a map from the tangent space to the cotangent space because it's a two form. So that map, you can invert it because omega is non-degenerate. That will go from cotangent to tangent. You can apply that to dH. So, and that will be a vector field because that's in the tangent space. So we will denote that by xh. This is a vector field, and this thing we call the Hamiltonian vector field associated to the Hamiltonian function h. So for any function on our manifold, we can, out of this function, we can construct a vector field by means of using this symplectic form omega that we call the Hamiltonian vector field. Because it's a vector field on a manifold, you can also think about it as a differential equation or as a system of differential equations. When you write your vector field in local coordinates, you look at the flow of this vector field, that's just differential equations. So the main example here, which kind of motivates this whole thing, it comes from classical mechanics. So we can consider a particle which moves in n-dimensional space. So this q is coordinates in that n-dimensional space. You know, so q is kind of a vector, q1, etc., qn. And then we want to, so suppose this particle moves in a potential force field, then the equation that describes the motion is that the second derivative of q is equal to the negative gradient of the potential function. That's Newton's second law, assuming that the mass is equal to 1. So this equation, it can actually be represented in that Hamiltonian form that we introduced. To do this, well, this is a second order differential equation, so to make this to turn this into a vector field, we need to make it first order. So we introduce additional coordinates that we call p. So p is the velocity, p dot is equal to q. Yeah. That's right. P is q dot, thanks. So P is the velocity, and if we do that, so now we are on a 2n dimensional manifold. We have P coordinates and Q coordinates. So we are now in R2n with coordinates P and Q. In this R2n, we can consider a symplectic form, which we write as dp dq. So this dp dq is actually a sum dp1 wedge dq1 plus dp2 wedge dq2 and so on. And on this 2n dimensional manifold, we consider the function which in physics is called the total energy. So the energy is 1/2 p squared. That's the kinetic energy. Again, p squared actually stands for the sum p1 squared plus p2 squared and so on. And you add the potential energy, that's the total energy. And then because we have this symplectic form and this energy function, then out of these two things we can create the corresponding Hamiltonian vector field. And if you do the calculation, then you'll see that the Hamiltonian vector field is exactly the Newton equation. Well, it will be written in a slightly different form. It will be first order system, but this first order system corresponds to that second order differential equation over there, which is, so basically this whole idea of Hamiltonian systems is just another way, a more geometric way to think about Newton's second law, if you like. And also, well, usually this is done in a more geometric setting, so this particle doesn't have to live in Rn. It can live on a manifold. So initially, we start with a manifold, and then instead of going from Rn to R2n, one considers the cotangent bundle of that manifold. There, one has same kind of a symplectic form, same kind of energy, and again, Newton's second law on a manifold can be written as a Hamiltonian vector field on the cotangent bundle for that manifold. So that's the motivation where the notion, that's where the notion of a Hamiltonian system comes from. So now that we have this, we will discuss the notion of an integrable Hamiltonian system. We'll see what that is and why these systems are interesting and important. So in general, Hamiltonian systems, as any differential equations, they don't behave in a nice way. They're very chaotic. Integrable systems are those that do behave in a somewhat regular way. And in the Hamiltonian setting, this notion of regularity or integrability, this can be made very precise. So basically what we'll require is that our system has sufficiently many conservation laws. So as we know, in this setting of the Newton equation, as we know from physics, the energy is always conserved by this differential equation. So we will require here that there are sufficiently many functions that have the similar property of being conserved along the flow. And in that case, we'll call the system integrable. So to make this precise, we have our symplectic manifold, m omega. There we have a Hamiltonian function h, from which we produce this vector field xh. And now, well, what is a conservation law? So a conservation law is another function, f, such that if you evaluate this f along a trajectory of the field xh, that should be constant. So in that case, we will call f a conservation law. Also, conservation laws are known as first integrals. And thanks to this, these systems which have a lot of this will be called integrable systems. So the condition for being a conservation law, well, one can say that f is constant along trajectories, but actually this can be written in the infinitesimal form. Specifically, we take the differential of the function f, we evaluate that at our vector field xh, that's supposed to be 0. Because this thing that I wrote, that's just the derivative of the function f in the direction xh. That has to be 0. Sorry, I still need to figure out how this works. So this is the condition for being a conservation law. Actually, this can be written in a slightly different form, because recall that xh, we define it as omega inverse dh. So here what we're doing, we are taking dh, we apply an omega inverse, and then we're also pairing that with df. This expression can actually be written in a different form, namely it's omega inverse of dh and df. So what is written here, omega was a 2 form on a manifold, so it's a bilinear form on the tangent bundle, it's a bilinear form on tangent vectors. Because it's non-degenerate, you can invert it, and the inverse of a bilinear form on tangent vectors is a bilinear form on cotangent vectors. So omega inverse is what's called a bivector. It's omega was 0,2 type tensor, this is 2,0 type tensor. So we see that the condition for being a conservation law is that omega inverse of dh and df is equal to 0. So this expression here, it's has a, well, it's very important, and because of that, there is a special notation for it and a special name. It's called the Poisson bracket of H and F. So this thing here is called the Poisson bracket. And we see that, well, the condition for being a conservation law for a function is that its Poisson bracket with the Hamiltonian is equal to 0. With f is a first integral. This happens if and only if the Poisson bracket of our energy function and f is equal to 0. So one thing that we immediately see from there, omega was a skew-symmetric form, so omega inverse is also skew-symmetric. So if for f you take h itself, that's definitely 0, because you are evaluating a skew-symmetric, it's a Poisson bracket of h and h. But this Poisson bracket, it has a it's skew-symmetric because of the way it's defined. So in particular, we see that energy is always preserved along its own Hamiltonian flow, which of course, well, physically it's obvious that energy should be preserved, but this also holds for arbitrary Hamiltonian flow. So we know that the Poisson bracket of h and h is 0, so h is itself a first integral. In general, well, that's it. We don't have any other first integrals for a Hamiltonian system, and we'll call a system integrable if it has more first integrals. Specifically, it has, so to say, the maximal possible number of them, and the precise condition is as follows. So we say that xh is integrable. So loosely speaking, integrable is a lot of first integrals. And this first integrals, so as we just discussed, being a first integral for a function f, that means that the Poisson bracket with the Hamiltonian is 0. But we will actually require more. So if you have any first integral, its Poisson bracket with the Hamiltonian is 0. But it turns out that it's important that if you take two first integrals, their Poisson bracket with each other should also be 0. So we will require that. What it means that, well, any of these conserved quantities you can interpret as a Hamiltonian, consider the corresponding flow. So all these functions that we consider, they should be conserved quantities for flows of each other. So xh, we're going to call it integrable in the following situation. So we should have a bunch of first integrals with the condition that the Poisson brackets are 0. By the way, when the Poisson bracket is 0, one says that two functions are in involution with each other. So that just means 0 Poisson bracket. And we will say that a Hamiltonian system is integrable if it has a bunch of first integrals. They are in involution. And also we want to have a maximal number of such functions. And maximal, what maximal means depends on the dimension. So suppose that we are on a symplectic manifold. Recall that the dimension of a symplectic manifold has to be an even number. So we are on a symplectic manifold m to n, the dimension is 2n. In that case, it's a pretty easy exercise in linear algebra that if you want to have a bunch of functions, well, of course, you can have infinitely many functions that are in involution. Just take the Hamiltonian and repeat that infinitely many times. That's stupid. You don't want that. You want functions that are what's called functionally independent from each other. None of these functions should be expressible as a function of other functions. And if you have such, then it's an easy exercise that at most you can have 1/2 of the dimension of the manifold. That's pretty straightforward linear algebra. And in that case, we will say that it's an integrable vector field or an integrable system. So xh is integrable on m to n if it has maximal, and maximal means equal to n number of first integrals in involution. Yeah, independent. That's independent. First integrals. In involution, yes. So independent means that you cannot express any of them as a function of the other ones, or you can take the differentials of those functions at a generic point. This should be linearly independent. So in that case, we call it an integrable system. One should know that there is no one absolutely standard definition of an integrable system. Sometimes people will require some additional conditions, but this condition is what's included in pretty much any definition of an integrable Hamiltonian system. So for example, note that, so as we'll see, so in a few minutes, I'll state a theorem that says that if you have this condition, then the corresponding differential equation can always be, in some sense, just explicitly solved. So these are very nice systems that you can solve. So as an example, one can note that if n is equal to 1, if you are in a two-dimensional manifold, then, well, any Hamiltonian system is integrable. So xh is integrable for any h. Just for dimensional reasons. In this case, you need one conserved quantity. You have it, it's the energy. And yes?
It is the same that this gives you just a foliation by Lagrangian submanifold.
Yes. So that's...
because you have a regular mapping to Rn, yeah, so
Yeah, we will, in a few minutes, I'll state a theorem that describes the structure of this system. Yes, that's it. So basically, this tells us that if we have, for instance, a Newton equation on a line, then we can always solve it explicitly. That's kind of a standard exercise in any first class in mechanics is solving Newton's equation on a line. So why do we? And of course, this example is trivial. We'll have less trivial examples later on. Actually, this KdV equation, which will be our main example, of course, corresponds to n equal to infinity because that's an infinite dimensional integrable system. We'll get to that later. First, let me state the main result on this finite dimensional integrable systems. So let me note one thing, that in this course I'm not trying to be super precise. So for some theorems I might miss some technical conditions. So don't judge me for that. That's not because I'm ignorant or stupid, but I'm just trying to save some time. Yes?
The case n equals to 1. This formally doesn't satisfy this condition if Hamiltonian is not regular.
Yeah, sure. I mean,
if Hamiltonian has critical points, then
GH is not equal to 0 almost everywhere. It's a strange energy function if it does not satisfy that. So, but yeah, sure. Thanks. Okay, so now here's the main result on integrable Hamiltonian systems, which is called Arnold-Liouville theorem. I'll state it. You'll tell me right away that it's wrong. That's, of course, intentional. So in this here, we suppose that XH is an integrable system with integrals. When I say integrals, I mean first integrals f1, etc., fn. By the way, since we know that the energy itself is always a first integral, when we say that there are n integrals in involution, one can always assume that one of them is energy. So for instance, f1 is equal to h, because that's always present. So assume that we have an integrable system with n first integrals, and the first claim, well, of course, what we can do, if one has a first integral is a function that's preserved by the flow. What you can always do, you can take the level set of the function, restrict your flow. That's kind of the intention. Well, that's the whole point of first integrals. If we have n functions, they're all preserved. One can look at their joint level set. That's a half-dimensional submanifold, generically. And that is preserved by the flow, of course. But that's not the point of the theorem. But the point is that joint level sets of f1, etc., fn, we know that they are invariant under the flow, but the theorem says that actually these are very simple submanifolds. Specifically, these are invariant tori. So it's not just some n-dimensional manifold, but it has to be a torus. It's
manifold.
Yeah, one needs to assume some compactness assumption needs to be made here. Either M is compact, or that the map defined by this n functions is a proper map, some of those.
In R2n you have counterexamples.
Yeah, sure. It's our invariant tori as long as they're compact. So the technical statement is that if you have a regular level, joint level set and it's compact, then it's a torus. So in general, of course, a joint level set of n functions could be any n-dimensional manifold, but here the claim is that it's a very simple n-dimensional manifold. It's a torus. Also, if you care about symplectic geometry, then you could say it's a Lagrangian torus, which means that the restriction of the symplectic form to that is 0. We don't care about that too much because we want to study dynamics. So that's the first claim. Well, so far it's not very interesting. Okay, it's a torus, so what? We need to say something about the dynamics. The claim about the dynamics is as follows. So you have this n-dimensional torus. On this torus, you can introduced coordinates that are defined modulo 2 pi. These are the angle coordinates on a torus. Of course, there are infinitely many different ways to choose such coordinates, but the claim is that one can choose the angle coordinates phi 1, etc., phi n on the torus, in which the flow of our Hamiltonian vector field becomes very simple, namely phi 1 dot is equal to a constant c1, phi 2 dot is equal to a constant c2, and so on. So the flow, the differential equation becomes an almost trivial differential equation with right-hand sides being constant. Of course, this is very easy to solve. If phi 1 dot is equal to c1, then phi 1 is c1 times t plus another constant. So in this form, we can immediately solve our differential equation. And it becomes trivial, and we see what the solutions are. Well, if this was in Rn, the solutions would be just straight lines. Solutions to this are straight lines. Because we are on a torus, solutions are going to look like this kind of curves that go around the torus. In general, these are these irrational windings of the torus. So that's the second claim of the theorem, that there is a special choice of coordinates in which the flow takes this super simple form. And part 3 is that, well, thanks to this special choice of coordinates, one can actually explicitly solve the initial differential equation, whatever that means. So xh can be solved. Any differential equation can be solved by the existence theorem, but that means that one can solve it in a more or less closed form. You would say, well, that's obvious because, well, we already solved it, right? Phi 1 is equal to c1t plus another constant. Of course, the non-trivial part here is that, well, we had some original coordinates from them. We passed to this new coordinates, and the question is, well, how explicit this passage is. But the claim is that it's rather explicit, and because of that, one can go to this new coordinates, solve a new coordinates, then revert to the original coordinates again using somewhat explicit formulas, and therefore solve the initial equation. Yes?
Do you mean xh can be solved by quadrature, maybe?
Yes, that's, yes. So technically, the claim is that it can be solved by quadratures, which means that, well, the operations that you allow, in addition to standard arithmetic operations, you allow taking indefinite integrals, you also allow inverting functions. So using these operations, you can solve. Yes.
Of course, we can solve by quadratures if we know these first integrals explicitly.
Sure.
Yeah? Because sometimes people say that, of course, if there exists some first integrals in involution, blah, blah.
Quadratures in terms of those functions.
Yeah, but we must know them to solve. Yeah?
Yes, you need to consider, it's, you can express your solution in terms of those functions using quadratures. That's the claim. In reality, what this means is that usually you can solve these systems using some kind of special functions. So in examples, these are elliptic functions, abelian functions, something like that. So the solutions are actually rather complicated, and this theorem, making it effective is very difficult. So it's not that you can, it immediately tells you what the solution looks like. It's a complicated procedure. But in addition to just being solvable, this part 2 tells us that the dynamics of the systems is very nice. It's very regular. It's this nice curves on tori. That's pretty far from what solutions of general differential equations look like, which are crazy, chaotically behaving curves that are super sensitive to initial conditions. This is quite the opposite of that. Yes.
Some systems have more than n integrals. They are not in involution.
That's right.
For example, the Kepler system has this Lenz-Runge vector.
Yes.
What is the role of this superfluous or this? Does it look like?
It means that your solution will. So in general, well, typically if this number is C1, C2, and so on, they're not immeasurable, then you have trajectories that are dense on the toroid, but it might happen that actually trajectories feel smaller dimensional toroid. That's exactly the situation you are describing. Because if you have an additional conserved quantity, you can restrict to the level sets of that. That will describe you a subtorus of this. So that's what happens in Kepler's system.
The Hamiltonians of these first integrals, they also generate a group. Is this of course now no longer abelian, so not torus?
No, but
what this group is?
It might not be even a finite dimensional group. But for the Kepler system, yeah, it's probably something simple. It's a three-dimensional group. It's something like the standard solvable three-dimensional Lie group that's called Sol. I think it's something like that. I don't remember exactly, but in general, it doesn't have to be, because when you take a Poisson bracket of two Hamiltonians, it's again a Hamiltonian, but it's a function of the initial Hamiltonian, so altogether this might give you an infinite dimensional group. But the joint level sets are still tori, that's the point. And they will be tori of smaller dimension.
Yes. Can you remind me of your definition of invariant torus? Does this mean that like your level set, your fixed joint level set, is an embedding of n-dimensional torus into your space such that every point of this set still stays on that embedded torus along your Hamiltonian system?
Invariant means invariant under the flow. So that means that our vector field xh is tangent to that torus, and as a result, when you solve the differential equation, if you start from this applies to any joint level set. So whichever point in the phase space you take, or on a dense subset of points, because some level sets are singular, they're not submanifold. But you take a generic point, it will lie on some n-dimensional torus, and it's going to be invariant, so you're going to stay on it.
Will it be not that, like a kind of fat toroid?
Would it be what?
Not that, like a.
Oh, yeah, sure, yeah. There's no claim on what the embedding of the torus looks like. It can be, yeah, the embedding can be pretty complicated. Yeah. No restrictions on what it is. You can take any torus you like, build a system that's going to have that as an environment.
But anyway, it exists, right?
Yes.
Okay, thank you.
Okay, so this is what we'll mean by an integrable system, and let me mention some examples. So as we mentioned, in the number n is called the number of degrees of freedom. The dimension of the phase space is twice that number. Basically, recall that in that Newton's law example, we start with a manifold like Rn, it's n-dimensional, then we double the dimension. So the number of degrees of freedom is actually the dimension of the physical configuration space where our system moves, and when we double it, it's because we add velocities or momenta to this initial coordinate. So, and we noted that if we have 1 degree of freedom, then it's always integrable, because we only need one conserved quantity, and that's the Hamiltonian, which is conserved, so no problems there. If we go to higher dimensions, then integrability is not given, so generally one doesn't have it, but sometimes one does, and the simplest case where we see integrable systems is when we have some kind of symmetry, and the symmetry forces integrability. So for example, we can consider a particle in R2 which is moving in a potential field, but this field is not just potential, but it's what's called a central potential field. A central force field is a force field such that you have a fixed center, and then the potential is constant on circles centered at that point. So the potential only depends on the distance from the fixed point. It's rotationally symmetric. So particle in R2 in central force field. So such a thing is always going to be integrable, and the integrals here, well, first we have the energy, or the Hamiltonian, that's preserved, that's one integral, because here the particle in R2, our symplectic manifold is R4, one needs two integrals, so in addition to the energy, we need one more. And here, by the way, note that the condition of being in involution is trivial because every first integral is always in involution with the energy. So that we don't need to care about. And the second integral here is what's called the angular momentum. So if here the coordinates are q1 and q2 and the corresponding velocities are p1 and p2, and the angular momentum is something like this. And you can verify explicitly that due to rotational symmetry, this thing is going to be preserved. For that, just take the Poisson bracket with the Hamiltonian. Show that if u is the function that only depends on the radius, then this Poisson bracket has to be 0. Of course, there is a deep explanation for that. That's called Noether's theorem, which says that symmetries always lead to first integrals, but also here you can just do an explicit calculation, see that that's preserved. One example of particle in R2 in central force field is Earth moving around the sun. Of course, Earth is not in R2, but you can consider two-dimensional plane that contains the orbit of the Earth, restrict the motion to that plane, then it will be exactly an example of this kind. Actually, well, it's a kind of a very special example because, as Peter mentioned in that example, there is actually an additional conserved quantity, because here Arnold-Liouville theorem will tell us that solutions live on two-dimensional tori. But as we know, Earth actually moves along an ellipse around the sun, so it's a one-dimensional curve. That's due to the presence of an additional conserved quantity here. But it's because Kepler's law is very special. So Kepler's law tells us that the gravity force is proportional to 1 over radius squared. If you change that second power of the radius to anything else, then this breaks down. It still remains an integrable system, but if the gravity would be proportional to 1 over r cubed, the Earth wouldn't move in closed curves. But instead it would fill two-dimensional tori as it's supposed to by Arnold-Liouville theorem. Okay, so I have until 10:30, right? Okay, so in this last few minutes, yeah, but that includes questions, huh? Okay, that's good. Yes, so now so we define these Hamiltonian systems in the setting of symplectic manifolds. However, and we'll be talking about KdV equation, as also happens with many other integrable systems, a more appropriate setting is what's called Poisson manifolds. So what is a Poisson manifold? So we define on a symplectic manifold, we define this Poisson bracket of two functions, and we define it by inverting the symplectic form. That was the definition of a Poisson bracket. The notion of a Poisson manifold you get if you write down the axioms that the Poisson bracket satisfies, but then forget that it comes from the symplectic form. And the axioms are as follows. So first of all, the Poisson bracket is skew-symmetric. Then the Poisson bracket is bilinear over real numbers. You compute the Poisson bracket of f alpha g plus beta h. That's alpha fg plus beta fh. And the second property is that the Poisson bracket satisfies what's called the Jacobi identity. You take the Poisson bracket of f and g and then the Poisson bracket of that with h, and you cyclically permute these three things. There are three ways to permute them. You add these three terms together, that's equal to 0. That's called the Jacobi identity. Altogether, these three properties, they tell you that functions on our manifold with respect to the Poisson bracket, they form a Lie algebra. So these functions form a Lie algebra with respect to the Poisson bracket. There is actually one more property that tells us that this Lie algebra structure is compatible in a nice way with multiplication of functions. Namely, if we compute the Poisson bracket of f and gh, that satisfies the product rule for the derivative. That's fg times h plus fh times g. And that easily follows from the Poisson bracket being defined as omega inverse applied to two differentials. We know that differentials, they do satisfy that product rule. And now, well, what we can do, we can say a manifold is a Poisson manifold if there is an operation on functions that satisfies these four properties. And then in general, we'll see that it doesn't have to be given by this formula. It no longer has to be a symplectic manifold. However, what it will always be, it will be given by a formula like that, but here instead of omega inverse, we'll have some bivector pi. But the thing with this pi, if pi is invertible, then we can go back. We can invert pi, we can say that let omega be pi inverse. And in that case, it will be a symplectic manifold. But the problem that in general pi might be degenerate. So the notion of a Poisson manifold is more general than the notion of a symplectic manifold. However, there is a general structural result on Poisson manifolds which says that, well, suppose you have a Poisson manifold, then it doesn't have to be a symplectic manifold. However, it's always a union of symplectic manifolds. So in this Poisson manifold, in general, what it will look like, this manifold will consist of smaller submanifolds, which are called the symplectic leaves, and they will be symplectic manifolds. And the way the symplectic leaves are typically described is as follows. So suppose you have a symplectic manifold, you take a function f, you compute Poisson bracket of this function f with other functions. Then if you have a symplectic manifold, it cannot happen that this is always 0. If you have a non-trivial function, then its Poisson bracket with other functions cannot vanish identically. However, for a general Poisson manifold, this can happen, and such functions f, they are known as Casimir functions. And in general, what Poisson manifolds look like, they're as follows. So there is a bunch of Casimir functions. You find all these Casimir functions, then you can restrict your Poisson structure to joint level sets of these Casimir functions. And when you do it for all Casimir functions, these joint level sets, they turn out to be already symplectic.
Would be no globally defined.
Yeah, it's true locally, yes. Globally, it doesn't have to be true. In examples we'll consider it will be. So here is an example. So we will define, in R3, we'll define a Poisson bracket. It cannot be symplectic because the dimension is odd. And the Poisson bracket will define it by the following formulas. So the Poisson bracket of x and y is equal to z, and then you just cyclically permute x, y, and z variables. So the Poisson bracket of y and z is equal to x. The Poisson bracket of z and x is equal to y. So this is, so one can see that this is, well, of course, here we define Poisson brackets just for coordinate functions, not for all functions. However, using this product rule, this allows us to extend the Poisson bracket to all functions. One can see that this satisfies all the axioms of a Poisson manifold. And for this Poisson structure, I claim that x squared plus y squared plus z squared, that's a Casimir function. So what that means is that the Poisson bracket of this with any other function is equal to 0. For example, let's take the Poisson bracket of this with x. So the Poisson bracket of x squared and x, that has to be 0, because by the product rule, that will reduce to 2x times the Poisson bracket of x and x, that's 0 by skew symmetry. So that's 2y bracket of y and x plus 2z bracket of z and x. Bracket of y and x is negative z. Bracket of z and x is y. So we see that that's indeed 0. And clearly, same thing is going to happen if we compute the Poisson bracket with y and z, because there is clearly symmetry here with respect to this cyclic permutation of variables. So x squared plus y squared plus z squared is a Casimir function here, which means that we can take the level set of that function. It's a sphere, and we can restrict our Poisson bracket to that sphere, and one can do it and then show that on the sphere this actually becomes a symplectic structure. So on the sphere it's already non-degenerate. In fact, on a sphere we have a 2 form, which is just the area form, so it's unique up to a factor rotationally symmetric form on the sphere. If that Poisson bracket is restricted to the sphere, one just gets that area form on the sphere.
Plus, where even local Casimir functions don't exist. So I think the more geometric definition of the symplectic leaves is just to call them orbits of Hamiltonian vector fields. Oh, yeah. So without any Casimir function, these are orbits of.
Well, they will exist near.
Because Casimir functions even locally could.
Well, if you take a maximal rank point and near that point, they will exist.
Yeah, at some points, yes, but.
Yeah, sure. Yeah, I mean, you are right that this definition doesn't always work. However, there is a way. It is always true that any Poisson manifold is foliated by symplectic submanifolds that are called its symplectic leaves. Okay, so yes.
Symplectic form look like at the origin.
At the origin, we have a 0-dimensional submanifold, which is a point. On that 0-dimensional submanifold, we have the only symplectic form that exists there. That's trivial form because there are no tangent vectors, so there's only one bilinear form on a 0-dimensional vector.
The sphere of radius 0.
Yeah. So, but yeah, technically any point is a symplectic manifold in a unique way. So the symplectic leaves can be zero dimensional. Yeah, they can be of any even dimension, including 0, which is an even number.
And also, like, are you kind of assuming that like the space of polynomials in RC is kind of like a dense in the space of like smooth functions with respect to some topology, so that you can talk about only like polynomials?
Well, that's a good question. So as was said, one can prove that any Poisson bracket is defined by the formula f bracket of f and g is pi of df dg. And it's sufficient to know Poisson brackets of coordinates to find pi, because the matrix of pi in coordinates is just its entries are pairwise Poisson brackets of coordinate functions. After which you know pi, you can compute it for any function.
It's easy to write down pi in this case.
In this case, pi is 0, z, negative y, negative
And as a bivector.
yeah. Sure. It's a matrix of that bivector in x, y, z coordinates. You can write it as a bivector also.
So you have 3 minutes.
Okay. Yes. So why do we care about Poisson manifolds more general than symplectic manifolds? Well, symplectic manifolds, they naturally arise from physical considerations. When you have some physical system, you supplement your coordinates with velocities, then on that manifold we have a natural, or momenta, we have a natural symplectic form. That's a non-degenerate Poisson manifold. However, there are many systems where, for different reasons, the appropriate Poisson structure is degenerate. For instance, that naturally happens when we have a system that has some symmetries. A natural thing to do when you have a system with symmetries is take quotient by the symmetries. You can start with a symplectic manifold, take a quotient with respect to a symmetry, and then the manifold you end up with is not going to be a symplectic manifold anymore, depending on how you take that quotient. And that's going to be a Poisson manifold. So for instance, one example of an integrable system is just a free rigid body. So you have a solid that's kind of free to move in space, that has a lot of symmetries, in particular rotational symmetry. You can mod out that rotational symmetry, after which the equations of the free rigid body, they will be written as Hamiltonian equations with respect to this Poisson bracket that I wrote here. So this Poisson bracket naturally arises when you have an SO3 symmetry. This actually should remind you of defining relations for the Lie algebra. SO3, that's not accidental. This is a Poisson bracket that arises from SO3 symmetry. And when we'll be talking about KdV equation in the next 2 lectures, we'll see that, well, the Poisson bracket that's, well, there will be actually 2 Poisson brackets related to that equation. None of them are symplectic structures, but they will be Poisson structures that are degenerate and have this Casimir function. And I think I'll just stop here. And that's, we will still be kind of using some finite dimensional ideas in the next 2 lectures, but mainly we'll be talking about the infinite dimensional set. Thank you.
Let's say.